Welcome back, dear students. This is second session of chapter 1, real numbers. Correct? What have I written on the board? Milli. Well, I dedicate this word to Madhav Sadesai, who had given this word. And what does it mean? Milli. M, most. I, important. L, lesson. L, learnt yesterday. Most important lesson learnt yesterday. Now, yesterday means when in the previous session, right? Okay. So, let's recall what we learned in the previous session. First, we learnt definition of factor. Second, definition of multiple. Third, how to find factors of a number. Fourth, how to find multiples of a number. And fifth, the last we saw was finding prime factors. From that, pairs of factors, and from pairs of factors we find all factors of a given number. Alright? Do you remember what I said? We will make application of these pairs of factors in factorizing a quadratic polynomial. But that is in the second chapter. I don't want to waste time here in the first chapter doing that. In near future, I'll be uploading the first two chapters of standard 9. In the second chapter, polynomials, all kinds of factorizations are there. So you can watch that video of standard 9. Today, I'll proceed further and see how we find HCF. Okay? Okay? Finding HCF of prime by prime factorization method or using fundamental theorem of arithmetic. Excuse me. Now, you know how to find prime factors of any composite number. But now, what do you mean by fundamental theorem of arithmetic? We should see that first. Okay? So, just observe and understand. What do you observe here? I've written 4 numbers. I can write more numbers. Alright? What type of numbers are this? I'll give you a hint. Are they prime numbers or composite numbers? Correct. They are all composite numbers. Observe further. What have I done? I have obtained the prime factors of 20. Can you say with me? 2 into 2 into 2 into 2 into 2 into 2. What are these? The prime factors of 64. Come on. 2 into 36. 36 further. 2 into 18. 18 further. 2 into 9. And 9 is 3 into 3. 108. 2 is a factor of 108. So 2 into 54. But 54 being composite, I won't write that. What is 54? 2 into 27. What is 27? 3 into 3 into 3. If I write more composite numbers, I can express their prime factors. I can obtain their prime factors. So, what do you observe here? I've taken composite numbers. Correct? We obtained its prime factors. On left hand side you have composite number. On right hand side you have its prime number, prime factors. So look at this, prime factors of 20. Then look at the prime factors of 64. 4 numbers are given here. So 4 prime factors are on right hand side. Compare any two or compare any one with the other 3. What do you find? Are prime factors of this 20 and 64 the same? Sure? No? Yes? Not the same. Prime factors of 64, are they same with the prime factors of 72? Once again, no. So, what do you find? The factorization, prime factorization of every composite number is unique. Correct? Now, one more thing you see. Instead of 2 into 2 into 2, if someone writes 2 into 5 into 2, is this prime factors in red box and the black box the same or different? Same. It doesn't make any difference. Can you tell me which property of real numbers is used here? Correct? The order is changed. Commutative, associative properties, if you remember. Further, well, all the prime factors in the red box, they are unique. They are not same. Can I express this in some other way? Somebody may write 3 into 2 into 3 into 3 into 2. What we have in the red box? Prime factors of 108. What we have in the black box? Prime factors of 108. Are they same or different? Same. Only the order in which the prime factors are written is different. Correct? Okay. So, what we observed, did you understand? Can we put it in the form of a statement? Once again, I will help you. What we had taken here? Composite number. What we observed? They can expressed as a product of prime factors. Yeah, they can be factorized in the form of prime numbers. What else? That expansion, that expression, that multiplication is unique. Let us put that in the form of statement. Every composite number can be expressed or factorized as a product of prime numbers, and this product, expression is unique. Sorry. from the order in which they occur. The order may be different. So apart from the order in which this prime factors occur. So that was the statement given by Friedrich, not fried rice, huh? No more Chinese things now. Friedrich Gauss. This statement was framed by Friedrich Gauss, and it came to be known as fundamental theorem of arithmetic. Well, you learnt about Euclid in 9th standard. Do you remember? Yes. Euclid had actually first observed this, but in proper statement form, it was given by Gauss. So Gauss gave the fundamental theorem of arithmetic. That is nothing but writing each composite number as a product of its prime factors. Did you get it? So now we are going to find HCF using fundamental theorem of arithmetic, which is nothing but obtaining prime factors of numbers. Clear to you? Good. Fine. So now what is the question? Obtain HCF of the following numbers. Question. Obtain HCF of the following numbers. First, 20 and 36. Now, how to find HCF? Well, I'll obtain the prime factors of 20 first. Alright? 2 tens are, 2 fives are, 5 ones are. Clear? Then let's obtain the prime factors of 36. 2 18s are, 2 9s are, 3 3s are, 3 1s are. I think this work you can do very easily. Now I am going to note down the prime factors of 20, or write down that 2 into 2 into 5. Then of that of 36, 2 into 2 into 3 into 3. See children, what I am doing? I am going to underline the common factors. 2 is a factor of 20, 2 is also a factor of 36. One more time, 2 appears to be common factor. It is common. Anything else? 5 is present here as factor of 20, but 5 is absent as a factor of 36. So it's not common. So what is common? Children, I'm going to write one more time. 20 is equal to, what is product of underlying factors? 4 into 5. Well, 36. What is product of underlying factors? 4 into the one which are not underlined, its product 9. Here you have to observe this 4. Therefore, HCF of 20 and 36 is 4. And one more thing you have to observe. You have to look at HCF from different angles. Then you will understand the application of HCF. When we are going to see that later, you will understand it better. Okay, especially in the word problems. Okay, so this you have to visualize HCF from one angle, and that is when any number, look here, these two composite numbers, how their pair of factors are written. Only one pair of factor is chosen such that one factor is common. And observe here, what is HCF of these two other factors of 20 and 36? Now, This, if you find HCF, it is 5 into 1, and 9, it is 3 into 3 into 1. Correct? So HCF is 1. When HCF of any two number is 1, they are called co-primes. They are called co-primes. Alright? So 5 and 9, they are co-primes. Now look here. 20 is equal to 4 into 5. 36 is equal to 4 into 9. This is the highest common factor of 20 and 36. And the remaining two factors, they are co-primes. So in that situation, 4 is said to be HCF of 20 and 36, as I have written here. Children, what I mean to say here, say suppose 20, if I write 2 into 10, that is correct. 36, if I write 2 into 18, that is also correct. But here I cannot say 2 is HCF of 20 and 36. Why? Because the other factors, they are not co-primes. Look, 10, that is 2 into 5. 18, that is 2 into 2 into 3. Well, something is common. The HCF of 10 and 18 is not 1. It is other than 1, so they are not co-primes. Are you getting my point? See the basics, see the fundamentals, children, here. So, here 4 can be said as HCF of 20 and 36. This is viewing HCF from one definite angle, which will help us later. Okay? Well, this you got. This is one method. Maybe I have complicated, but we are not going to use this method. We are going to use method of prime factorization, fundamental theorem of arithmetic, and we are going to do it differently. But once again, I showed you this because we are going to apply this somewhere in the word problem. Okay? Chal. Again, something to be observed here. Let me say this 20 is unknown by writing x. This 36 is also unknown by writing what? Is equal to. This is A. This is also A because it is same. Into B into C. So when you have these two equations of this form, x is equal to A into B and y is equal to A into C, where A is highest common factor of this, then B and C are co-primes. And in this case, you can say A is HCF of x and y. Whenever you come across this type of situation, you can say A is HCF of x and y. Look, one more example. P is equal to M into D. Q is equal to M into K. What can you say here? M is HCF of P and Q. Provided that D and K are co-primes. Clear to you? Okay. Now see, I'm going to use find HCF in a different way now. And for that, I need to recall or revisit powers and exponent. Do you remember somewhere in 6th or 7th standard you learned? Observe and understand. Let's recall. Three into 3, 3 into 3 into 3, 3 into 3 into 3 into 3. It's getting boring now. It is tedious work. I'm making my work tedious. This verbally you can say 3 appears once. What you can say here for this? How can you speak out? 3 is multiplied with itself 2 times. 3 is multiplied with itself, correct? 3 times. 3 is multiplied with itself 4 times. Now if I have to write 3 into 3 into 3 into 3 into 3 into 3 100 times, writing is very tedious. Yes, very laborious, correct? You will not like to write 3 into 3 into 300 times. But if you speak 3 is multiplied with itself 100 times. Okay. In few words, you can say that. 3 appears once, 3 is multiplied with itself 2 times, 3 is multiplied with itself 3 times, 3 is multiplied with itself 4 times. Even if 3 is multiplied with itself 1000 times, you can say it very easily, 3 is multiplied with itself 1000 times. Mathematicians were not satisfied even by this brief statement of these expressions. I can write like this, 3 into 3 into 3 into ... 100 times. Correct? Utna brief kiya. But mathematicians wanted still a briefer form, briefer expression of this. So I'll start with this only, the last one. They played a trick. They used very nice trick. A box. Okay. Which number is repeatedly multiplied? 3. They wrote in this box. And just above the box, to its right corner, they put a small box. How many times is 3 multiplied with itself repeatedly? 100 times. So they wrote 100 here. How many times 3 appears? Okay, what is multiplied? 3. What is multiplied? 3. What is multiplied with itself? 3. What is multiplied with itself? 3. How many times 3 appears here? 1. How many times 3 is multiplied with itself? 2. How many times 3 is multiplied with itself? 3. How many times 3 is multiplied with itself? Now you see this. How many times 3 is multiplied with itself? 100. Look at this, children. So briefly, they have written the long multiplication. Very lengthy multiplication is expressed in the shortest way, briefest way. Well, what are these brief expressions called? They did not exactly call them as powers, but I'm going to call them as powers for our convenience. I'll say all these are powers. What I'm going to say? They are all powers. 3 raised to 1, 3 squared, 3 cubed, 3 raised to 4, 3 raised to 100. They are all powers. You have already learned them. I'm going to call them as powers. Now, as a body has different parts, this powers also has or have 2 parts. One is the bigger box at the bottom. That is called base. That is called base. Why? Because that is basic thing in this expression. If I don't write 3, nothing is there. Basic thing in this expression is 3. So 3 is called base. And how many times it is multiplied with itself repeatedly? God knows. 1 time, 100 times here. But what is that called? This you understood, base, that literary word, that is the basic requirement in this expression. So it's called base, but this is called, they called it index or exponent. Now why they called it, I don't know. क्या ऊपर है? Somewhere in Latin word or in a Greek word, that index means upper. Index means up, upper part. God knows. Anyway, but every power you can say has 2 parts. Power for our convenience we are saying. Otherwise, this number is read as 3 to the power 1, 3 to the power 2, 3 to the power 3, 3 to the power 4, 3 to the power 100. Or 1th power of 3, 2nd power of 3, 3rd power of 3, 4th power of 3, 100th power of 3. So power word is used while speaking. But they are not called power. But for our convenience, I am going to call them as powers. Okay. This square, 2 and 3 have special sayings. Like square of 3 are 3 square. Cube of 3 are 3 cube. Instead of saying 3 raised to power 2, you can say 3 square. 3 raised to power 3, instead of that you can say 3 cube. Okay. But then For rest, you have to say 3 raised to whatever power it has. So understood what is base and what is index? This is either you call index or exponent. Fine. I hope you observed and understood that we are going to use in this method. See, I won't write this lengthy form. Now you have learned how to brief it. 2 is multiplied with itself 2 times. So I am writing 2 square into 5. Correct? Here 2 square into 3 square. Here you may write 1 if you want. Even if you don't write, it is understood. Correct? Thus, HCF, capital, small, anything you can write, HCF of 20 and 36 is equal to. Children, now it's a different story. Here you have expressed 20 as product of 2 powers. I said I'm going to call this power 2 square and 5 raised to 1. 36 also is expressed as product, multiplication of 2 powers. Now look at the powers. Observe the powers having common base. 2 square and 2 square, that 2 is the common base. I'll underline that. Anything else? Your power with base 5 is there. But there is no power having base 5 here. In the second number there is power with base 3. But there is no power with base 3 in the first number. Only the powers with same base are to be chosen. Okay? Chal. Now what is HCF? For that we have to look at the exponents. Yeah, index. What is the exponent of underlined power? 2. What is the exponent of this underlined power? 2. 2 and 2. Which is smaller out of the 2? They are same. So you can write, you can choose 2. Actually you have to choose the smaller one from the 2 indices that I have circled. Which is smaller one? They are same. So you can say 2 is smaller. So base is 2 and the smaller index is 2. What is 2 square? 4. That is the HCF of 20 and 36. Got it? We'll take another example. Alright. Which method is employed here? Correct. The fundamental theorem of arithmetic or finding HCF by prime factorization method. The second example, obtain the HCF 72 and 108. Obviously, you have to find the prime factors of 72 as well as the second number 108. 2 36s are, 2 18s are, 2 9s are, 3 3s are, 3 1s are. 2 54s are, 2 27s are, 3 9s are, 3 3s are, 3 1s are. Correct? Let us write down the factors of 72 and 108. But I am going to write in which form? Product of powers. Okay. How many times 2 is multiplied with itself? 3 times. Into 3 is multiplied with itself 2 times. So 3 square. Next, how many times 2 is multiplied with itself? 2 times. How will you write briefly? 2 square. How many times 3 is multiplied with itself? 3 times. How will you write in brief? 3 cube. Very interesting, children. You got the GCD now. GCD means HCF. Thus, HCF of 72 and 108 is equal to, what do you have to do now? Yes, underline the powers with same base, like base. Base is 2, base is 2. So you may underline that. Correct? Now look at the exponents. 3 and here 2. Which is the smaller one? 2. So choose the power with smaller index. Which one? The underlined power which is at the bottom. What is that? 2 square into. Yeah. Go further. Proceed. Oh, here the power with base 3 is also common. But for HCF, You have to consider smaller index. Choose the power with smaller index. Which is that? Look, index is 2 and 3. Which is smaller? Correct. 2. So 3 square is the power with smaller index. Now multiply. Nothing else is there. What is 2 square? 4. What is 3 square? 9. And what is 4 nines are? 36. Clear to you? So what is the HCF of 72 and 108? 36. By which method we have found the factors? HCF using prime factorization method or using fundamental theorem of arithmetic. Can we take 3 numbers? Okay. Third example. Finding HCF by arithmetic, by using the theorem, fundamental theorem of arithmetic, is difficult when it comes to 3 numbers. Let's see. 64, 72 and 108. So we will have to find factors, prime factors of 3 numbers this time. 2 32s are, 2 16s are, 2 8s are, 2 4s are, 2 2s are, 2 1s are. Correct? 2 36s are, 2 18s are, 2 9s are, 3 3s are, 3 1s are. I hope I am not too fast. Anyway, you can do this. 2 54s are, 2 27s are, 3 9s are, 3 3s are, 3 1s are. Well, I am not going to write all prime factors. I am going to write product of their powers. Well, all are 2's. 2 is multiplied with itself 6 times. Only one power. 2 raised to 6. 2 is multiplied with itself 3 times. So that is 2 cubed into 3 square. 2 square into 3 cubed. Okay. Now it is very interesting. Alright, thus HCF of 64, 72 and 108 is equal to dash. Let's see. Choose the powers with like base, same base. Power with base 2, power with base 2, power with base 2. Remember, it has to be common in all 3 numbers. Yeah. Here, power with base 3 is common only in 2. In the first one, it is not existing. So, you don't have to choose those powers for finding HCF. Alright. Then the same story. Look at the power, exponent, which is the smallest one. Very good. 2. So, 2 square you have to choose. That power with smallest index is 2 square. So, what is HCF? 4. HCF of 64, 72 and 108 is 4. Clear to you? So, got how to find HCF?